Now, first, let's talk about normalization. What is it? Normalization is a concept that is used typically in databases and data warehouses where you focus on meeting certain design key points. Oftentimes, normalization involves breaking down tables into smaller data sets. Breaking this down is taking out redundancy, and then when we are working with smaller data sets, they're easier to manage. It's a lot easier to work with 5 tables that have maybe 10,000 rows than one table that has 50,000 rows in it. This just makes it easier for design. On top of that, normalization is there to prevent what are called anomalies. Now, what is an anomaly? Anomaly is a random occurrence, something you don't know about, something that you don't want to have happen but still happens. In this case, we have update, insert, and deletion anomalies. Now, what we mean by these anomalies is, let's say you have an improper table that isn't normalized or designed correctly. Let's say I perform an update and I only want to change one row. Well, if I have a bad table design, when I go to change one row, I might end up changing 10. Same thing we said for insert and deletion anomalies. If I go to make a deletion or an insert, let's say something goes wrong, and then suddenly I have several different changes where I only wanted one. So normalization is good at preventing these anomalies because what it does is isolate data so that when you do a change, you don't suddenly have a ripple effect, and then it doesn't affect multiple rows instead of the one you just chose. So this is the main concept behind normalization. Taking data, breaking it down to smaller data sets that are easier to manage, preventing strange things from happening in it, and then just having control over the data and its design. Main goal of normalization is to focus and reduce redundancy, as well as create well-structured series of tables without errors or inconsistencies or anomalies. Now, what is redundancy? Redundancy is when you have many parts of a table repeating for maybe only one column. For example, let's say we have student, student name, student ID, and then course. Now, every student is going to take multiple courses, right? So let's say we have an improperly designed table, and one student is taking 5 courses. So this would say student ID, student name, course number 1. Student ID, student name, course number 2. Student ID, student name, course number 3. Student ID, student name, course number 4, and so on and so forth for every single student. Now, the course is changing, but the rest of the columns aren't. So for this one change that happened, we are now repeating multiple values in the rest of the table. This is called redundancy. This is what we aim to avoid. Now, there are many different reasons to avoid this. One of the big reasons is each one of those values takes up space. So if for one student we suddenly now have 5 rows, well, that's 5 times the amount of data that we originally needed. So this is going to kind of pose a little bit of an issue, especially in the long run. But another goal of normalization is simply to increase the speed and optimize the data. So that way, when you write a query, the data is sorted in a nice, efficient manner, and it's easy to fetch that information. Now, when should we normalize? Normalization isn't a mandatory process. However, it is highly recommended to do. There are pros and cons to the normalization concept, and here we've listed a couple of them. First of all, normalization is an expensive process, and by expensive we mean it's going to take you more time, more effort to actually go through and normalize different things. Designing can be difficult when we take normalization into consideration. Having to go from one table to suddenly 5 is going to take more work, having more keys, more relationships, different degrees, and different designs. Normalization is also good for final designs, but not for ones at the beginning and testing. Normalization, let's say we're in data modeling and we try to perform normalization in conceptual and logical models, that's not really going to be a very good design. It's going to put too much stress and too many issues on the tables as we create them. However, for a final design, that's where it's mainly met at. With the process of normalization comes more tables. With more tables comes more keys, more relationships to show, and more columns and designs. So this obviously will take more time to do. And then lastly, one of the other things to think about is that when you do a join or you combine tables in SQL Server, this is going to be rather costly. This takes time to do. So we have to be considerate of thinking how many tables we have for the process and are they really needed. So normalization isn't something that's mandatory to do, but it is something that is recommended because most of the times the benefits outweigh the costs. However, at times the cost can be higher, in which case you should avoid normalization. We have to look at what are functional dependencies. Functional dependencies are referring to how do attributes actually relate in a table. In prior sessions to data modeling, we were comparing tables to other tables, but now we're going to focus on one table and its individual columns. Functional dependencies tell us how do these columns actually relate to the rest of the columns on the table. For a well-designed table, functional dependencies should rely on the primary key and candidate keys. To designate these different columns, we typically associate the term prime attribute with primary key or candidate keys. All those who are not primary keys or candidate keys are labeled as non-prime attributes. And functional dependencies tell how do non-prime attributes relate to prime attributes. Now, there are quite a number of different dependencies and different models to look at. What we'll do is we'll take a look at three of the most common ones that we see in data modeling. We have full dependency, partial dependency, and transitive dependencies. In full dependency, that means that whatever attribute you're looking at, whatever column, relies fully on the primary key in place. So, for instance, maybe student name and student parking spot would rely on student ID. So you can't show what the name of the student is without the ID, and you can't tell what parking spot they have unless we have ID as well. Partial dependencies are when you have non-prime attributes that don't depend on all of the prime attributes listed. What we mean by that is, let's say perhaps we have let's say a spouse table. In the spouse table, we'll have it for the employees. So in this table, we would need to have an employee ID and a spouse ID. If there's any column in there that simply depends on only one of those keys, it's considered partial. So in the example using a spousal table, we have a spouse ID, we have an employee ID, perhaps we have name, and then we have maybe address and workplace. Let's say for a spouse table, we keep records of where the spouse works. Now, this would depend solely on the name of the spouse or whoever the spouse is. It wouldn't depend so much on the ID of the employee. So in this case, this might be seen as a partial dependency. Transitive dependencies are when you have an attribute that doesn't directly depend on a prime attribute, but instead depends on another non-prime attribute. So, for example, if we look at the example below us, we see that there is a last name. This last name depends on the author number, but the author number depends on the ISBN. Or we can also take a look at how the publisher and last name or royalty or edition depend on the book title. And the book title itself depends on the ISBN. So there we might also see a transitive dependency. Here are some more examples. Let's say we use the same schema for each one. Report card. For a full dependency, if we look at the example next to it, we see that the grades you get on your report will have to do and use student number and course number. You can't find out what grade someone got if you don't know what course they took, and you can't find the grades for a person if you know the courses, but not the person. So this is fully dependent on both of those keys used. For a partial dependency, using the same schema, we see that we have title and last name. Now the title and last name for the course depends on the course number, but this has no connection to the student number. This is a partial dependency. It's still using one of the prime attributes, but not all of them. And the last one we have listed is transitive dependency. Here, we see that course number will dictate last name. And for some reason, last name will dictate the room number. In this, we see that room number does not directly depend on the course number. Instead, it depends on last name. So this is labeled as a transitive dependency. Now, how do dependencies affect normalization? How do they dictate what we do and don't do? The types of dependencies each show how a column relates to the rest of the data within their own table. If we have good data and a good table design, all of the data should be identified with the prime attribute. So dependencies, in a way, can help you decide what normal forms to use. If you see in your table that you have transitive dependencies, that might be an indication that you have not reached the proper normalization level. Now, normal forms are a part of the normalization process. Going through the normalization process, you break things down into several formal steps. These are the normal forms. We've already discussed a little bit about normalization and how the process of it is made to reduce redundancy and to eliminate any repeating values and then organize and break down the data into smaller tables. Well, this is not a process we simply do in one large take. This is broken down into several different steps. Each one of the steps is referred to as a simple normal form. Most commonly, you'll see companies that go to 1NF, 2NF, or 3NF. First normal form, second normal form, and third normal form. However, there are many other variations and continuing forms after this. We have elementary key normal form, Boyce Codd normal form, or 3.5 as it's also known, floor normal form, fifth normal form, domain key normal form, and sixth normal form. For the purpose of the video, we'll only be focusing on the first, second, and third, as they are the most common and frequent in the data modeling process. First, we'll discuss the first normal form. The first normal form has a main focus of taking away any redundancies that are seen throughout the table. You find and remove redundant values, oftentimes simply by breaking a large table into smaller ones. In this example, we see the values as they are constantly repeated. In product category, hardware is repeated 4 times, while software twice. Product group, we see CPUs repeated 3 times, operating systems repeated twice. Brand, we see AMD repeated twice. And then after that, we have more specific unique values. The fact that hardware and product group categories are always repeating is posing a little bit of an issue. In normalization, we discussed how redundancy can simply take up extra space than we need. And here we do see hardware repeated 4 times, which means it's taking 4 times the space. So, to break this up or to fix this issue, we will separate this table into 2 other tables, or possibly 3 or 4, depending on how far you want to go. When we break a table down, let's say for this example, we break this product down and we have the brand, name, and price. Then we have product group in one table, and then product category as another. Now when we have one table as brand, name, and price, we can include something in there that will point to the product group of that. And in the product group, we will only display CPUs, mainboards, and operating systems. Lastly, for product category, we can have that in its own table, in which case we will display 2 values, hardware or software. To move in the second normal form, we have a few criteria here. First of all, you must meet all the requirements of 1NF, which means the redundancy must be taken care of. After you've maintained and fixed that issue, we can now move to the next step. Here, we are making sure that all non-prime attributes are fully dependent on the prime attribute. If you recall from an earlier video, prime attributes are the attributes that stand as keys or as candidate keys. Non-prime attributes are all those who do not. So in this example, we see student, courses, and instructor. The student has student name and address, which does take precedence in using enrollment number. Course name needs the course code, and office needs the instructor name. So in this example, we see that it has been broken down into the different sections, there's little chance for redundancy, and we see that most of the non-prime attributes are dependent on the prime attribute. Finally, in third normal form, we go through and make sure that we have no transitive dependencies. First requirement, though, is to make sure we meet 1NF requirements, 2NF requirements, and then after that we can proceed. Here we have met 2NF requirements and made sure that everything in here is directly dependent upon a prime attribute. However, what if that prime attribute is not in fact an actual key, but another column? Here we see, for example, course name depends on course code, but that course code depends on the unit code. So indirectly, course name depends on unit code. This is a transitive dependency. This is what we seek to eliminate in this section. So in third normal form, we seek out these transitive dependencies, and we can break them down again into their own table. In this case, we might take the course name and put it in its own table and give it a foreign key pointing towards course code or unit code. Here we have a normalization example going from unnormalized to first NF, second NF, and third NF. We see project code, project description, customer number, customer name, staff number, staff name, grade, and number of days. Now, first off, we might see that there is some redundancy here, right? So if there's a different project with different customers, that means every time a new customer or project comes in, the staff names will have to be repeated. So, in order to remove this redundancy, in 1NF, we see that the project, description, and customer name have been broken into their own table, whilst the rest of it, project code, staff, staff name, grade, and number of days, have been broken into theirs. In 2NF, we seek to make sure that everything in those tables properly are fully dependent, or dependent at least, in part to the prime attributes. Project description depends on code, customer name depends on code, and customer number depends on code. However, we might see a little bit of an issue in this one because we see customer name might depend more on customer number. So this might have a transitive dependency there. We see project code and staff number and number of days. And lastly, we see staff number, staff name, and grade. Now in 2NF, all of the columns that are listed do depend in some way on a prime attribute, but it may not be the correct prime attribute, as seen in customer name depending on customer number. When we move into 3NF, we take care of this. As you can see, the project code, which we noticed had a transitive dependency, has been broken down now. From project code, we have project description with customer number, and customer number and customer name now have their own table. Project code, staff number, and number of days are its own, and then the staff number, staff name, and grade are its own. By the time we reach 3NF, we've taken one large table and broken it into 4 smaller ones. But now, those 4 smaller tables all have data that specifically relates to the prime attribute or key being used for that table. This normalization method is what we do in order to advance our data set, optimize our queries, and better control the data. Instead of dealing with that large table in the beginning with all that information, we now have 4 smaller tables with less columns. So in a way, this helps us as far as our wanting to deal with this project.